Today we are talking about antennas, and we're going to do a bit of a deep dive into all of the different things that make up an antenna's performance. We're going to talk about SWR, explain what it is and how it affects an antenna. We're going to talk about directivity, gain and antenna's efficiency. Hopefully by the end of this video you will have a better idea of all of the elements that come together to make up how an antenna actually performs in the real world, and have a better idea of what to look for when choosing an antenna. Now, just before we jump into it, I want to say a massive thank you to Hugo over at TrueRC. If you don't know who they are a manufacturer of some of the best quality antennas in FPV. A lot of the info I have in this video has actually come from TrueRC's website. Not only do they sell their own products on there, but they have a fantastic blog section where they provide a lot of info to the community as well. And if you're interested in checking out their products, all that information, there is a link to it in the description of this video. Also, I want to say, if you do find this video interesting, please do check out the link in the description to my Patreon. I would not be able to keep making content like this without the support of my patrons, and I want to say a massive thank you to everyone who does support the channel on a regular basis. Anyway, let's get on with it and let's talk about SWR first of all. We're going to start with what is VSWR, or what is also known as SWR. The term stands for voltage standing wave ratio, and it is basically the amount of reflected power back to the source. If we take a look at this little diagram on the bottom right hand side, you can see here we have a little video transmitter with 100 milliwatts of output. We have our coax cable, and this little line up here is our antenna. For the purposes of this first demonstration, we're going to assume that this is the perfect antenna, and as you can see in that scenario, all of the power from the transmitter goes up to the antenna and all of that power is radiated out as radio waves. However, the reality is there is no such thing as the perfect antenna, and every antenna has a tuning for the specific frequency you've got it on, and depending on how well it is tuned will depend on what its VSWR value is. For instance, if we take a look at this calculation here, you can see an antenna with a VSWR of 1.9 to 1 in a 100 milliwatt output would have 10 milliwatts of reflected power and 90 milliwatts of potentially radiated energy. That would mean 10% of the power our transmitter is sending out is being reflected back and lost, and what will happen is that power actually reflects back to our transmitter, and that results in the transmitter getting hotter, potentially then also in extreme cases burning out its output transistors. As I said, in the perfect world, every antenna would be perfectly matched, and the perfect antenna would have an SWR of 1.0 to 1. However, reality is that doesn't really exist. Now, you will hear many people say an antenna with an SWR of over 1.5 to 1 is a bad antenna. However, that really isn't the case. It is possible to have antennas with SWR as high as 5 to 1 and that be absolutely fine, because there are many different things that come into play with regards to antennas, and it's not just about the VSWR. There are things such as efficiency, which we will come on to later on in this video. Now, because SWR is based on an antenna's tuning, it is frequency and bandwidth dependent. For instance, the antenna that is best tuned to the specific frequency you're transmitting on will have a lower SWR, but that doesn't necessarily mean it's going to work across the whole band of channels you're transmitting on as well. There is a balance to be had between an antenna's SWR and tuning and its bandwidth, and you can have some antennas that have a very wide bandwidth and a medium SWR, or an antenna with a very, very low SWR but a very narrow bandwidth. Now, SWR affects both transmission and reception. In transmission, we have seen it affects the amount of RF energy that is actually being converted into radiated radio waves, whereas in a receiving situation, it is actually how well the antenna is matched to our load or our receiver, or how close to 50 ohms the antenna's impedance is. Now, just showing you this chart here from a VNA, you can see we have an antenna here with an SWR that is really right down to here, And at that point there, it is 1.10, which is a very, very low SWR. But if we look at the bandwidth of the antenna, you can see that it actually increases very, very rapidly. You can see it goes up there and it goes up there. And this antenna you're seeing here is actually one of the TrueRC antennas that I have shown down here. It is always worth taking into account that VSWR is not a measure of one antenna is better than another. It is a measure of how well the antenna is tuned to the frequency that you're working on. It is good to tell you if an antenna is damaged or not, but it is not a strict measure of one antenna being better than another, because there are other factors that you have to take into account, such as antenna efficiency, directivity, and gain. You can see on this chart down here, which was provided by TrueRC, that the SWR in relation to the power emitted isn't as big as people may think. For instance, an SWR of 1.5, we still have over 91% of the power transmitted compared to an SWR of 1.02. There is a balance to be had here with regards to SWR and antenna efficiency, and we'll come on to that a little bit more in a minute. But an antenna with high SWR still could be better than an antenna with low SWR if the antenna is more efficient overall. Looking at this antenna on the VNA, it would be very easy to think that this antenna is only going to work well at this point here, with the SWR is at its lowest. That is at 5820 and it is 1.10. If we then look as we move down the band and up the band, it very quickly gets up to sort of 1.5, 1.6 towards 1.8. And it would be easy to think that you should only use this antenna on this frequency here, which is 5820. Yes, as you move down, the SWR increases, but the amount of power you're losing isn't dramatic. If we see here on the chart at 1.5, we are still radiating potentially 91% of the RF energy we're sending in, compared to 1.02 at 95%. So whilst you can see the antenna does have a narrow bandwidth, that doesn't necessarily mean it's going to be poor performance as you move either side of its lowest point. Now, measuring SWR can be done with various pieces of equipment. You can use a VNA or an SWR meter. In ham radio, it's fairly straightforward to measure SWR with an SWR meter. At the frequencies we tend to use in FPV, things do get a little bit more difficult, but you can get some VNAs from the likes of Amazon and other places that will give you an indication. However, you shouldn't take those pieces of equipment as strict fact, because the very, very good lab equipment costs many thousands of dollars. Another term you may hear alongside SWR is S11, or what is known as return loss. It is another expression of SWR, but it is a measurement of the loss of power as a result of the SWR level. It is generally used in more technical aspects of measuring antenna performance, but it is probably a better way of understanding how an antenna is actually performing from a tuning point of view. For example, we could have a VTX with 100 milliwatts of output attached to an antenna of an SWR of 1.9 to 1. That would mean 100 milliwatts goes in and 10 milliwatts is reflected back. That 10 milliwatts is 10 times less power than was put in, so it would be shown as minus 10 dB on the S11 chart. That would mean there would be 90 milliwatts left to be potentially radiated from the antenna, depending on what its actual efficiency was. As you can see, an S11 chart is just another way of describing the effect that SWR has on the antenna's performance. Now, as we touched on a little earlier, what affects SWR is the bandwidth of the antenna, or what is also known as the tuning. Now, this is the range the antenna is designed to operate in at the best possible efficiency, in the sense of the lowest SWR range. If we take a look at the antenna I've got shown here, you can see that bar there and that bar there would be classed as the antenna's bandwidth, and that is where you would have an SWR within the range the manufacturer has recommended. Again, as I said earlier, just because we've moved outside of that lowest point down here doesn't mean the antenna's not going to operate well. It will work over a bandwidth up to a point, and then it would be outside this bandwidth that we would see the biggest losses of the antenna. But in this area here, there wouldn't necessarily be a dramatic difference in the actual performance, even though you can see the SWR is changing. Now, none of what I've said means you should ignore VSWR. It just means it should not be the driving factor when choosing an antenna. You can obviously get improvement by choosing a better antenna for your system. It is simply about choosing an antenna that is actually balanced everything overall and not just very low SWR, because there are other things such as gain, efficiency and directivity that all have a massive effect on the antenna's performance. If we take a look here at this chart from TrueRC, we can see we have here two X-ear antennas. We have an X-ear 1 and an X-ear 2. You can see both the antennas actually are not at their peak tuning in the band that we use, which is the ISM band. Their peak tuning is actually at 6 gigahertz, but they both have a flatter curve here within the ISM band that we're using. Because this is an S11 chart, remember below -10 was at least 90% power, and we're right down here at an average of -17.54 for the X-ear 1 and -18.11 for the X-ear 2, meaning the X-ear 2 is going to offer some better performance, but both antennas are still very good, even though their peak tuning is actually out of the band that we're using. Now, the reason the section that we're using on the ISM band is actually outside what you would say is the peak SWR tuning is that isn't necessarily where the peak performance of the antenna is. As you can see, if you look at the chart, it actually looks a little bit like a W, with the section of the ISM band we're using right in the middle of that W. And this is the point where the antenna has its best circularity, and that is going to offer the best performance overall. Again, remember where I've said it's not just about SWR, it's also about all of the other factors as well, and this is a classic example of that. When choosing an antenna, it's hard to know what the best tuning position for the antenna should be. Should it be at the bottom of the band or at the top of the band? And actually, VTX's output often varies with the channel selection as well. In my tests, it's often the case that digital VTXs tend to output the most power on their lowest channel, which is channel 1, but that isn't always the case. So again, there's always a balance to be had between choosing an antenna that's best suited for your system and best tuned for your specific setup as well. So that is VSWR, and as I've said, it is basically the amount of power that is accepted or reflected by the antenna due to its tuning. Now, there are many ways you can measure VSWR. There are very high-end pieces of equipment which cost many tens of thousands of dollars, but you can also get one of these, this cheap VNA that I've got here from Arnest, that allows me to measure VSWR on the bench. Personally, I only really use this to be able to look at how an antenna is performing compared to what I would expect. As I've said, whilst VSWR is important, it should not be the main factor you use for choosing one antenna over another. More than anything, it's a good way of being able to see if an antenna is damaged or not, especially when you can't see in it, such as like on these omnidirectional antennas here. However, you shouldn't be using it as a baseline factor to say one antenna is definitely better than another simply because it's got lower SWR. Now, in FPV, having bad SWR really doesn't have much of an effect simply because of the amount of power we're using. Even some of our highest output transmitters are still not transmitting anywhere near enough to cause any problems. In big ham radios or big transmitters, high SWR can have a detrimental effect on the power amplifier and even cause it to burn out, but that isn't really something we see in FPV, and even having an antenna with high SWR isn't going to cause any problems. Now, whilst SWR is important, it is not the only factor, as I've said, that affects antenna performance. And the next thing we're going to talk about is antenna efficiency, because this is just as important as SWR in many ways. As I've mentioned several times already, there are other factors alongside SWR that affects how well an antenna performs. One of these is antenna efficiency. Efficiency is the amount of energy that reaches the antenna that is then radiated as RF energy. If we take a look at our little diagram down here in the corner again, you can see we have our VTX, our coax, and our antenna. We can have our output go out into the antenna, and at this point there is no power reflected back, therefore all of the RF energy has reached the antenna, and we would assume that all of that energy is then being converted into radio waves. However, that isn't actually the case, because there are also losses within the antenna itself that causes you to lose energy and again affect the antenna's performance. These losses can be things such as ohmic loss, i.e. conductor resistance, so the resistance of the antenna's materials itself. Connection losses within the antenna, so if the antenna is made up of several metal parts and they are soldered together, there will be losses on those joints. We have lossy materials around the antenna itself, such as the plastic housing. Again, all of this will absorb energy. And then we have ground losses around the antenna too. So the easiest way to think of antenna efficiency versus VSWR, VSWR is the amount of energy that is actually reaching the antenna and not being reflected back or being accepted by the antenna. Then efficiency is the amount of energy the antenna is accepting that is then being converted into actual radio waves. Now this is where things get quite interesting and starts to show that SWR alone isn't the major factor that affects performance. For instance, we have two antennas here. We have antenna A, which has an SWR of 1.05 to 1 or an S11 of -30, and it has a 75% of radiation efficiency. And we have antenna B that has an SWR of 2 to 1 or -9.5 dB and 95% radiation efficiency. Both antennas are on 100 milliwatts, and antenna A is let in 99 milliwatts and radiated 74.9 milliwatts, but antenna B has let in less power, 88.8 milliwatts, but actually radiates away 84 milliwatts because it has much better efficiency over the first antenna. So this shows that you can have an antenna with a higher SWR, but if it is more efficient, it's going to provide better performance overall. Next thing I want to touch on is polarization. Now this is something that often confuses people, but the easiest way to think about this is how the radio waves are let off the antenna. For instance, we have vertical, horizontal, right-hand circular polarized and left-hand circular polarized. The easiest way to think of these is a bit like waves in the sea. So for vertical, you would have normal waves going up and down. For horizontal, you'd have waves going side to side. With regards to circular polarization, think of this like a thread on a bolt. So a left-hand polarization would be like a left-hand screw, and a right-hand would be like a right-hand screw. Now, the idea of polarization is that it allows you to match antennas together better, but also allows you to reject signals from other systems that don't match the polarization. There isn't a complete ignoring of those other signals. Your antenna would simply be less sensitive to those signals compared to the signals of the same polarization, and this is why we use it in FPV, allowing us to fly around other pilots with different polarizations, because it means that our antennas will be less sensitive to their signals and more sensitive to our signals. It simply means that we're going to be able to hear our signals better than the signals from the antennas that don't match on the same polarization. For us, when we use it, you should always use antennas of the same polarization style. You can use opposite polarization if you have to, but you will have much higher loss, and as a result of that, poorer signal. So when you are buying antennas, make sure that if you're buying them in pairs for your video transmitter, that you're either buying left-hand or right-hand circular polarized. Doesn't matter which, as long as you choose the ones that are matched together. So, antenna efficiency is rather an interesting subject and it isn't one you'll hear spoken about a lot, but it can have quite a large effect on how well your antenna performs. And in fact, when you look at the charts that I showed, it's easy to see you can have an antenna with high efficiency but poor SWR actually outperform an antenna with low SWR but poor efficiency. So again, it is more than one factor that will affect how well an antenna performs. Next, we're going to talk about antenna gain, explain what that is, and also explain how that has an effect on the performance of your antenna as well. The last big thing that has an effect on antenna performance is its gain. Now, gain is the term of how sensitive or how well the antenna performs compared to what is known as an isotropic antenna. An isotropic antenna is a hypothetical antenna that radiates the same intensity of radio waves in all directions. It, in theory, has the perfect radiation pattern, which means the signal is equally distributed in every direction, and that would be known as a gain of 0 dB. Now, gain is simply the ability of the antenna to radiate more or less in any direction compared to that theoretical isotropic antenna. If we take a look over here, we have what is known as a basic lossless dipole, and it is transmitting out its radio waves all around on each side. However, note at the top here and at the bottom here, we have what is known as the nulls. These are the areas of the antenna that transmit very little to no RF energy. As a result of that additional RF energy that isn't being transmitted here and here is being transmitted in these other directions, and that means that that antenna has a gain of 2.15 compared to that isotropic antenna which transmits in all directions with a gain of 1.0. It is not the case that the antenna is amplifying the signal, it is simply directing the available RF energy in a different direction, and as such, that means it's got more gain compared to that theoretical antenna. You can have antennas that are omnidirectional, which will have small amounts of gain, and you can have directional antennas that can have much higher levels of gain, 20 dB or more, again though, compared to that isotropic antenna. It's also worth noting that gain also has an effect on both bandwidth and VSWR, and all three of these things are very much linked together, and it is really a sort of a triangle that gain, VSWR and bandwidth all have an effect on each other, and there is no one antenna that is perfect. You simply have to choose the antenna that is best for your needs. Looking back at our transmitter and receiver, you can now see that we've got directional antennas and all of our RF energy is now being pushed towards the front, and whilst there will still be some very small amounts at the back, it's going to offer a much better signal for our receiver. Down here we have a typical antenna chart for a directional antenna. Here you can see that front lobe coming up, which shows us our very high gain all the way up to 15.5 dB at the front, but then at the back you can see the green chart really pulling tight, and we're going to have much less gain at the back end, and this antenna is going to be much less sensitive to radio signals from behind it than it is at the front. So again, we're going to have a gain of 15 dB over that isotropic antenna at the front, a much lower gain compared to that antenna, and actually much worse performance at the back. Something to really understand with antenna gain is the more gain will generally mean more antenna directivity. Omnis can have a gain somewhere between 1 and 3 to 4 dB, but once you get above that, you're then pushing into directional antennas, which are going to start to ignore signals from areas around the sides and the back compared to the front. In transmit, it means more of the RF energy is going to go out the front and much less out the back, and in receive, the antenna is going to be much more sensitive to picking up signals out front than back. So if you're flying in front of yourself, you're going to have good signal, but if you fly behind, it's going to be much worse. When looking to buy antennas, good manufacturers will always show you the performance of the antenna on a chart. There are two main kinds. You have the radiation pattern chart and you have the directivity chart or gain chart. Now, if we take a look at these Odin antennas on TrueRC, you can see that they actually show the radiation pattern down here, and this looks a bit like a donut, and this shows the area in the middle where this red has the most gain, and that falls off as it moves up the donut and around to the top, with the null at the top and the bottom of the antenna, as I showed you a little bit earlier. You can also see this expressed as a chart like I've put up here. This is more of a slice of this donut, but again, you need to understand that this is different to the chart that you will see that shows gain and directivity. What this is showing you is the radiation pattern of the antenna, where you're going to get the most gain and where you're going to get the nulls. Looking at some directional antennas from TrueRC, here we have the X2A. Now, the interesting thing with this antenna is there is a separate antenna called the XA2, which is very similar in performance, but actually has a key difference, and that is how it performs horizontally with regards to its viewing angle or field of view beam width. Now, there is a chart for this antenna that they show here as well, comparing it to others, and if I just put that full screen, you can now see them side by side. Now, when you're looking at a chart like this, you need to understand that 0 at the top here is the front of the antenna, 180 is the back, minus 90 left, 90 right. You then have the gain pattern of the antenna shown here, as well as sort of the directivity and the antenna's ability to receive a signal on its beam width. If we look at the X2A here on the left, you can see it has a very similar gain level to the antenna here on the right, both about 12 dB. However, the big difference is the width of this lobe at the front here compared to this lobe here. The antenna on the left is going to have a much better horizontal view performance compared to this antenna over here. Now, you will see that there are 3 colors of markings on the chart. The green is the overall performance of the antenna. So you can see this antenna has plus 12 dB at the front, comes round to the middle, and then comes in towards the back. There's a bit of a lump here where the rear performance does increase, but you would get the worst performance from this antenna on about 135 and 135 minus on that side there. The red and blue are the charts that denote the polarization performance. In this case, we're going to say it's a left-hand circular polarized antenna, and that would be shown in the blue. Again, you can see the performance is very similar up front to the green. The green is the overall performance. So on the left-hand circular polarized use, it would be absolutely fine. But if you were using it on a right-hand circular polarized pair, so your transmitter was left, your receiver was right, you would see that this here would be much, much lower. The performance when you were cross-matching the antennas is quite substantial. You can see the same over here on the XA2, that the performance is different between the polarizations. So when you are looking at a chart like this, you are not only looking at the directivity, but you're looking at the difference between the polarizations of the antenna as well. So, as you've seen, SWR, efficiency and gain all have an effect on how well your antenna will perform. Not one of them is more important than the other, and really more than anything, the message I have is it's not about choosing an antenna with the best specs, it's about choosing an antenna with the best specs for your specific needs. For instance, if you're flying long range out front only, something like the TrueRC XA2s I've got here are going to offer the best possible performance. However, if you're flying bando or you're flying around yourself, the XA2s are going to give you signal issues when you fly behind, and something like this basic Omni is going to give you better performance. It's about choosing the antenna for your needs and not just the one that has the best gain, the best SWR or efficiency. Now, when choosing antennas, you've also now got to take into account some of the other things that come into play, especially with digital FPV systems. Whilst we did have analog systems that had diversity and multi-mixing, digital is actually a different setup, and we often have systems with multi-in, multi-out, or multi-in, single-out setups. For instance, DJI has 2 antennas receiving and 2 transmitting. HD0 is all receive and can have up to 4 antennas on the module. And Avatar uses a 3 receive and 1 transmit setup. On DJI, it's fairly straightforward because you can put 2 antennas on the receive and 2 on transmit, and actually put 1 as an Omni and 1 as a patch, giving you the best overall setup. However, on the likes of Avatar, you've got to take a different approach because we've only got 1 antenna transmitting. So depending on your flight style, you would choose whether you want that to be an Omni, like I've got here, or whether you want it to be a direction antenna if you're flying long range. So again, it's not just about choosing the antenna with the best performance, it's about choosing the antenna with the best performance for your specific setup. Now that is pretty much it on this one. I want to say a massive thank you to Hugo at TrueRC. I would not have been able to make this video without their support, as well as the information on their website. If you're interested in getting yourself some high quality antennas for FPV, there's a link to them in the description. You can get yourself something like the TrueRC XA2s, the Singularities. They have everything you would need for your FPV setup. If you have found this video interesting, please do let me know in the comment section. I'm really interested in hearing your thoughts on this type of content. If you'd like to support us to be able to keep making content like this,